Now it's time to start considering enthalpy. So we talked about energy and we looked at work and we looked at heat. Now we're going to consider enthalpy. Enthalpy and energy are going to be very similar to each other, but when we start talking a little bit more in detail about chemical reactions, the distinction between enthalpy and energy is going to be important. So enthalpy, we're going to use this delta H for, okay? So to understand enthalpy, we need to start understanding some features that give us our enthalpy. So the first thing we want to talk about is what is called a state function. All right, so basically, and this applies to energy and enthalpy. What we look at is the current state of our system, not the path that we use to get there. All right, so what we're saying is that this is path independent. It doesn't matter how we got there. It only matters that we got there and whatever that final state is. So an energy is a state function. So, okay, I'm in my home office right now and it's kind of got a little bit of a weird setup. All right, so here's my office and here is the door. All right, so I have a desk. I have like a shelving drawer unit. And then because I work on lots of projects and my daughter tends to come in here and wants to work on projects with her mother, we have another table set up here. All right. And so my desk chair is right here. Okay. So I need to get out of my office. How am I going to do that? Well, the conventional way to get out of my office is to stand up from my chair and to come walk around. And boom, I get to the door. My kiddo, she likes a bit of an unconventional way of getting out of my office because she is little and she can still crawl around on the floor without problems. So my daughter, sometimes when she's sitting on my lap and I tell her, okay, it's time to leave the room, she will get up from the chair and she will crawl under the table and then go to the door. Okay, so either method, getting up and walking around or crawling under the table, gets us to the door. So it doesn't matter how we got there. What matters is that we got there. That's a state function. Okay, and so you can see here I've got a mountain. There's a straight shot up the mountain and then there's a windy path up the mountain. All right, one might take longer to get there, but at the end result, both groups, the straight up the mountain or the windy road group, managed to get to the top of the mountain. When we are looking at octane, which is one of the primary ingredients in gasoline, all right, I can put a bunch of octane in a trash can and I can light it on fire. Or I can pump gas into my car and I can start my car's engine and I can drive my car. It doesn't matter which method I use to react off that octane. What matters is that for 1 mole of octane, I'm going to get 8 moles of carbon dioxide, 9 moles of water, and I'm going to be at the same final energy state. Doesn't matter if I lost all of my energy as heat in my trash can fire, or if I lost that energy as work on the pistons of my car and heat. 2 different paths, or I'm going to cross this out. You know, my illustration here for each of these is 2 different paths. My path out of my room, 2 different paths. I'm going to change this. I'm going to say multiple. Okay, because maybe there's even more methods. I don't know, maybe I'm a mole person and I dig a hole into the center of the mountain and then I climb. I don't know. Anyway, you could still find another way up. Multiple different paths, same end result. And this is going to be really important as we consider all of this stuff. So when we look at what's happening like in a piston, all right, we usually have either electrical work or we have what is called pressure volume work. So if I have expanding gases that are pushing on a piston, okay, there's a change in volume. That change in volume pushes up, the pressure changes, and that's where we get the pressure volume. Okay, so the work is done on the surroundings. We get negative okay? Because remember, if we are doing work on something else, the system's energy is negative. And so we can take our delta E equation, which is our heat plus our work, and change it to our heat minus our pressure times the change in volume, okay? And so you can see here in this gray box, I have an illustration of a piston and that pressure volume work, okay? All right, and then you can see there's going to be a volume change. Now, when I consider my work and I look at things with that pressure volume work, okay? Let's say I'm doing a reaction, in a flask and I've poured two liquids together. Well, is there a large volume change due to gases changing? Well, there's not, especially if we're open and our system is open, right? And when I think about the pressure there, if I'm just doing it open, I'm just in room pressure. So if we're at a constant volume, if we're not doing a massive volume change, if we're not expanding gases, we get our W term starts to drop out and will equal 0 at constant volume. And so we get this right here. We get this delta E of reaction is equal to the heat at constant volume. Okay, well, that starts to simplify things a little bit too, right? And that leads us into our enthalpy. So we get little to no work done. So our enthalpy is essentially our energy. Okay, these are situations where we don't have gases. The number of moles of gas does not change. Or where we do get a change in moles of gas, but the heat far exceeds any change in pressure volume work. Okay, so this is the vast majority. Vast majority of chemistry, unless you're studying gases and stuff. Again, it's not all, but it's the vast majority of it. And it's certainly going to be the vast majority of things that you would encounter in a teaching situation. And so delta H is that change in enthalpy. And so when we're at a constant volume or a constant pressure, our delta H is just equal to that heat. And so we can use heat, we can use Q to track our changes in energy. And so as we get this right here, all right, we get this delta H is equal to the delta E plus the pressure volume work. However, if we're at a constant pressure there, then we just get that enthalpy. And so that vastly simplifies what we're looking at. Okay, and so enthalpy is our delta H. Okay, and so we can go back to our exothermic and endothermic processes. And instead of considering them in terms of energy, we consider them in terms of enthalpy. So like I look at process A, I have 1 carbon dioxide and 2 waters. I look at process A initial, 1 methane and 2 oxygens. If everything's gaseous, 1 plus 2 equals 3, 1 plus 2 equals 3. No change in the moles of gas. And so if my products have less energy than my reactants, final is less than initial, and so I get a negative delta H, and I get an exothermic process. Heat has been released. Okay? The opposite is true for an endothermic process. Some things I need to put energy into, like if I have solid ice and I need liquid water, that solid ice needs to take in energy so that it can melt down into liquid water. And so that's an endothermic process where my final enthalpy is greater than my initial enthalpy, because final minus initial, if this is greater than this, then I get a positive number. And so that is endothermic. All right, and so that is enthalpy, and that is what we will be considering when we think about what's happening in our chemical reaction systems.